Right, so titrations are something that we've used in the lab before, and essentially what it does is use the um, solution of known concentration. So in this case, it could be the base and the beer up top. And we use that to figure out the concentration of an unknown solution. So we could have an acid in the bottom, or we could have those reversed. But it's just a quantitative method that allows us to determine the concentration of that unknown solution. And in order to do that, we need to know when the reaction that we're interested in has essentially reached the equivalence point. So for an acid-base reaction, that's going to be equal amounts of acid and base. So that's what's known as the equivalence point. And to indicate that, we could use a pH meter. So on the previous one, we've got the pH probe in there, so we can see how the pH is actually changing as we add the base to the acid. So we can see initially 1.30, it's going to be a very low pH because it's acidic in the beaker. But as we add the base, we'll see that pH start to climb. And with that reaction, it is going to be a colorless reaction. So if we don't have a pH probe, another thing we could use is the pH indicator, which is going to give us two different colors depending on the pH of that solution. So with it, I don't know exactly what indicator this is, but it could be sort of this pinkish red color in the acidic solution. And then in the basic solution, it's going to be yellow. So we can use that to as an indicator, would suggest to indicate when that reaction has reached the equivalence point. With the indicator, though, it doesn't necessarily actually represent the perfect equivalence point. It's usually going to be pretty close, but what we use to describe the color change here is this is what's known as the endpoint. And we kind of just assume, if we choose our indicator correctly, we kind of just assume that the equivalence point and the endpoint are going to be the same. But the equivalence point is where we've got equal amounts of acid and base. The endpoint, though, is just where we see the indicator change colors. And when we're looking at a titration with a strong acid, strong base, what we're going to see is if we are titrating the acid, so if we're starting with the acid in our beaker or flask and we're adding the base to it, we'll see initially we're going to have a very low pH. And as we start to add the base, we'll see that the pH is only slightly going to increase. And the reason for this is because we've got a whole bunch of acid in the solution initially. So when we add a little bit of the base, that little bit of base gets neutralized. So we no longer have any base. And then we've got a little bit less of the acid. So that's why we see the pH start to slowly increase. But as we approach that equivalence point, we're running out of acid. So now as we get near this point, once we add a little bit more base, there's not really enough acid to neutralize it anymore. That's why we see the pH skyrocket here. So if you've ever done a titration, you may remember that it's sometimes difficult to actually get that endpoint correct because it's sometimes just going to be one or two extra drops that could really skyrocket that pH and have you shoot past the endpoint. But once we get to the other side here, the addition of more base eventually just sort of plateaus in terms of the pH, and we don't really see much of a change anymore just because that solution's already going to be so basic that the addition of a little bit more of the base isn't really going to affect it too much. And with this titration, we kind of have this sort of S-shaped curve here. But with these titrations, I meant to click through this as we were going. But yeah, as we get near that equivalence point, we see that pH is just going to increase rapidly. And then we ultimately see it's going to flatten out. But at this equivalence point, that's going to be where we have equal amounts of acid and base. And that's why with these strong acid, strong base titration, that equivalence point is going to be right at a pH of 7. Because at this point, we're just going to have the water as well as the salt that we formed. But with the strong acid, strong base, the ions of that salt, the cation and the anion, aren't going to change the pH at all. That's why it's going to be just directly at 7. But when we have a weak acid, weak base, what we're going to see is a slightly different shape to this curve. So we're going to start up a little bit higher in the pH just because it's going to be that weak acid. And then with the equivalence point, what we're going to see is, in this case, it's actually going to be a little bit above 7. Because as we add the base to this, what we're going to see is that hydroxide from the base is going to cause some of the weak acid to dissociate. So if you can see here, this is acetic acid, HC2H3O2. So it's going to be a weak acid. We're primarily going to have it as this substance. But as we add something like sodium hydroxide, we're going to have that sodium ion, we're going to have the hydroxide ion as well. That hydroxide ion is essentially just going to steal the hydrogen from this acetic acid. And what that's going to cause then is the sodium ion will still just be present, but now we're going to have that acetate ion in higher quantities. And that acetate ion itself is going to be basic. It's going to be the conjugate base for that weak acid. And since we're going to have more of that ion present now at the equivalence point, that's why we're going to see the equivalence point here is actually going to be a little bit above 7. Because at this point where we added equal amounts of sodium hydroxide and acetic acid or whatever that weak acid is going to be, we'll have additional amounts of the conjugate base. And that's why we're going to see the pH is just going to be a little bit higher here. But again, we see kind of the same curve with the equivalence point as we approach it. It's not quite as drastic. We don't see it shoot up from like 2 all the way to 10. Now we're just going from like 6-ish up to 10 maybe. So the steepness here just isn't quite as dramatic. And if we look at, I'll see it on the next one then. But like I said, what we're going to see here is a pH slightly above 7 because as we add that hydroxide, the weak acid is going to dissociate to form water and just that conjugate base. So because we're going to have extra of that conjugate base, that's why we're going to see the pH at the equivalence point is just going to be a little bit higher when we're looking at a weak acid strong base titration. And with it, you can kind of just also remember that because weak acid strong base, the base essentially is going to take precedent over the acid, so we're going to see a little bit above 7 in that case. But this is going to be the reaction that's causing that. And as that acid gets weaker and weaker, what we're going to see is the change near that equivalence point is just going to become less dramatic. So like I said, with the strong acid, that stays pretty low pH just until we basically get to that equivalence point, and then we see it skyrocket there. But with the weak acids, we kind of see it's something similar, but as it gets weaker and weaker, we see that dramatic steep piece just becomes less and less. And we can see the equivalence point itself is just going to be at a higher and higher pH. Okay. And then with a weak base strong acid, so in this case, the acid would be in the burette, the base would be in our flask underneath. That's what we're titrating. That's why we're starting with a higher pH in this case. And the red line is going to represent what we would have with a strong base, strong acid. So it's essentially the same thing we saw before. It's just we're switching what we're titrating. So that's why we kind of just see the reverse here. Now it's sort of like a Z shape or a 2 shape rather than an S, just because we're starting with the base and we're titrating with the acid. But with the weak base, what we're going to see is that pH now is just going to be a little bit below 7, because in this case, what's going to occur is when we add the hydrogen ion from that acid, it's then going to cause the base to produce the conjugate acid, and that's why we're going to see the pH decrease slightly there. So instead of being at 7 like we'd see with a strong acid, strong base, we see it just a little bit below 7 because we've got a strong acid with that weak base. So it's kind of the same idea as the strong base weak acid. It's just kind of reversed now because we're titrating the opposite. And with the polyprotic acids, so something that's going to have multiple hydrogen ions that can dissociate, what we're going to see if we were to titrate these, if we were to actually include a pH meter, we could see as we add additional sodium hydroxide, as we add additional base, we're going to see that the pH is going to increase. But with these polyprotic acids, we're going to have an equivalence point, or we're going to have this steep section for each of those different dissociations. So in this case, H3PO3 to H2PO3 minus, HPO3 2 minus. So we can see in each case we're releasing an additional hydrogen. And we're seeing that the pH increases because we're looking at the conjugate base in each case. So as we go from H3PO3, so this is going to be phosphorus acid, to the ion here, it donated a hydrogen. So now this is the conjugate base. This would then be the conjugate base of that. So we can see the increase in the pH just as we add additional sodium hydroxide there. And then with ionic compounds, we're going to see a lot of the times those are going to be soluble in water, meaning that they'll completely dissociate. But there's going to be certain ionic compounds that are going to be very, very low solubility. And with those ones, what we're going to see is an equilibrium like we have here. So we've got barium sulfate as the solid in equilibrium with the dissolved ions. And what this is going to be known as is the solubility product. So it's going to essentially show us how much of this substance, how much of those ions are being produced when we take the substance and dissolve it. And since it's the solubility product, that's why we're just going to call it KSP. So the SP is just solubility product. And if we look at this expression, we can see the barium ion concentration times the sulfate ion concentration. And if we go back to the previous one, the reason we don't have anything in the denominator here is just because this reactant, barium sulfate, is going to be a solid, so it's not going to factor into our equilibrium expression at all. As long as we have some of that present, we'll have some of the ions, but we just don't include the barium sulfate solid in the expression. So if we wanted to write the expression for calcium fluoride, if you want to take a moment to try that on your own, just pause the video like usual, because I'm just going to skip ahead and show how we would do it. But we want to think about if we were to take this substance and dissolve it in water, what ions are going to be produced. And with it, what we're going to see, and I'll do the double arrow, is we'll get some of that calcium. And since it's group 2, it's going to have a positive 2 charge. And with it, we'll also get some of that fluoride ion. But since the fluorine is a halogen, it'll be -1. So if we look at the formula, we've got 2 of those fluorines for every calcium. Calcium's +2, fluoride's -1. So we'll really need, whoops, that got real wonky. We'll need 2 of those fluoride ions for every 1 calcium. So when we look at our equilibrium expression, we'll focus on the products because this is going to be a solid. We don't include those in the expression, so we'll just focus on these. And when we look at it, since we've got 2 of the fluoride ions, we'll just make sure to square that piece of it. So that was our coefficient from the dissociation equation. So we just want to make sure to include that in our equilibrium expression for the solubility product. All right. So looking at this question, solid silver chromate is added to pure water at 25 degrees. Some of the solid remains undissolved, so this is going to be one of those low solubility ionic compounds. So when we add it to water, most of it is just going to sort of settle at the bottom. But there's going to be a small amount of it that actually does dissolve. And this question is saying that we leave it in solution, allow it to stir for several days just to make sure that we do ultimately reach that equilibrium. And then the analysis of that solution shows that we've got this concentration for the silver ion. Assuming that the maximum amount of this silver chromate dissolved, and then there was nothing else going on, so we didn't have any other substances that would produce silver ions or chromate ions, we want to figure out what the solubility product for this substance is going to be. So when we think about it, we want to think about what ions are going to be produced from this substance. And we've got them both listed here. But because we're going to get 2 of those silver ions, when we look at the um, um, when we think about the concentration, it's really only going to be half as much for the chromate. So because we get 2 silver ions for every 1 chromate, this concentration for the silver is going to be double what it is for the chromate. So when we look at solving for our solubility product, we want to think about this dissociation, 2 silver ions because it's going to be +1, and then just the single chromate. So our expression will be the concentration of silver squared times the concentration of the chromate ion. And like I said, since we get 2 of these for every 1 chromate, the chromate is just going to be half of this concentration. So 1.34 times 1.3 times 10 to the -4th. Half of that is just going to be 6.5 times 10 to the -5th. But with this expression, we just want to make sure to square that silver concentration just because we've got a coefficient of 2. So we really just have to make sure that we include that that piece twice, really. So we're just going to square it. So 1.3 times 10 to the -4th squared times 6.5 times 10 to the -5th gives us a solubility product for silver chromate of 1.1 times 10 to the -12th. And that just shows why this substance is going to have such a low solubility. This is a really small equilibrium constant. So in terms of this solubility, we're only going to have a little bit of it move to the right-hand side. So we're only going to get a little bit of these ions actually forming there. And with this one, just again, remember, since this is a solid, it doesn't factor into our equilibrium expression at all. So it doesn't actually matter how much of this we have, as long as there's some of it present. And with it, the KSP is sort of a indicator of how soluble something is. A larger KSP just means we're going to have more of that substance actually dissociate. We're going to have more of it actually dissolve. But it's not going to be the same thing as solubility. So KSP allows us to figure out the concentration of those ions, but the solubility actually tells us how much of that substance is dissolving per volume. So it's something like grams of solute per liters of solution. And if we want to relate these two, we can use the KSP to get the concentration of those ions, which is really just going to be the solubility in terms of moles per liter. We can then get grams per liter just by using the molar mass. So if we think about moles per liter, we want to get to grams. So if we want moles per liter to grams per liter, we've got to convert moles to grams. So we need moles on the bottom somehow. We need grams on the top. We can do that just by using that molar mass. Let's see an example of that right here. So with this one, we've got the KSP of calcium fluoride, 3.9 times 10 to the -11. Assuming that all we're going to have in this solution is calcium fluoride. So we don't have any other ions that are going to affect the dissociation here. We want to determine what the solubility of calcium fluoride is going to be in grams per liter. So if you want to try this on your own, you can. But the way that this is going to work is we can use this KSP. We can use the formula here to think about how this substance is going to dissolve, what ions are going to produce for the small amount of it that actually will dissociate. And then we can use that sort of dissociation equation along with this KSP to figure out what the concentration of those ions are going to be. And then using the molar mass and that concentration, we can convert it from moles per liter into grams per liter. So if you want to try that on your own, just pause it, kind of give yourself a little bit of a chance. But I'm just going to skip ahead and kind of just show the answer. So if you do want to practice first, do just make sure that you pause the video. But like I said, with the first piece, we need to figure out what the concentration of those ions are going to be. So we need to think about how is the substance going to dissolve. And calcium's group 2, it's going to give us a +2 ion. Each of those fluorides are going to give us -1, but we have 2 of them. So when we look at our equilibrium expression or our KSP expression, X is going to be the concentration for the calcium. But since we get 2 of these fluorides for every 1 calcium, that concentration would be 2x. And since we've got the coefficient there, we also need to square it. So what we're going to see in this case is the KSP is really going to be equal to 4x cubed. So 4x raised to the third power. And we've got the KSP. We want to solve for x then. We could just divide this by 4 and then take the cube root. But what we're going to see is that gives us a value of 2.1 times 10 to the negative fourth. So with it, we can then use that value. We can then use the molar mass, because if we look at the equation we have here, we've got moles per liter. And if you want to think about it, you can rewrite it so it's a little bit easier to kind of see the fraction. But we've got 2.1 times 10 to the negative fourth moles per liter times, times the molar mass, it is 1 calcium times or plus the 2 fluorines. So we've got grams per liter. And what we're going to see here is moles on top, moles on bottom is going to cancel. And we're just left with grams on top, liters on the bottom. That gives us the units we're actually interested in here. And with this, we can just use the 2.1 times 10 to the negative fourth. The fluoride ion concentration would actually be twice as large. But for this one, since the calcium is 1-to-1 with the original substance, we can just use that value as it is there. So what we're going to see is the solubility of calcium fluoride is going to be 0.016 grams per liter of water at 25 degrees C. Of course, it's going to change at a different temperature. And then when we're looking at factors that are going to affect solubility, so something like barium sulfate, similar to what we started looking at this chapter, the common ion effect. If we had, let's say, sodium sulfate, that would then dissolve to already give us some of the sulfate ion. So what we're going to see is that's going to affect the equilibrium, and we're not going to have as much of the barium sulfate actually dissolve in that case. So if we've got a common ion present, that's going to shift this reaction to the left-hand side. So we'll get less of this substance actually dissolving. And it doesn't matter which of the ions is present. Both of them would have the same effect of shifting it further to the left, giving us more of this intact molecule. And then with the acidic or basic ions, the pH is also going to be important. So if we look at something like we have here, it's showing magnesium hydroxide. It's going to be a weak base. But what we're going to see is the solubility of this is going to be increased in acid solutions, because if we've got that H plus there, what it's going to be able to do is essentially take some of this hydroxide ion, force this substance to dissociate. Because if we think about, let me write it here, if we think about the dissociation equation for magnesium hydroxide, we'll have Mg2 plus 2 hydroxides, 2OH minus. So with the acid solution, what we're going to see is if we've got H plus, what that's going to do is react with some of this free hydroxide. So it's going to decrease the amount of hydroxide we have here, which is then going to shift this reaction to the right. It needs to essentially replenish that hydroxide. So if we take these basic ions and dissolve them in acidic solution, we'll see the solubility is going to increase. And we would see the opposite, or the same, I guess, for an acidic ion in a basic solution. if we had something like hydrofluoric acid in a basic solution. Let's look at HF. What we're going to see is the solubility is going to be increased, because if we have this in a basic solution, we'll have some hydroxide available. That'll react with this H+, decreasing the right-hand side, so we'll be removing from the product side. We'll have to shift in that direction. So we'll get more of this hydrofluoric acid actually dissolve in that case. And in some cases, what we'll see is a complex ion can actually form. So if we look at this table here, and remember a Lewis acid, Lewis base, a Lewis base is going to be an electron donor. A Lewis acid is going to be an electron acceptor. So in this case, these metal ions are going to act as electron acceptors. So if we think about just the first one here, ammonia, we're going to have a lone pair on that nitrogen. So what it's going to do is that lone pair is essentially going to attack this silver, and we're going to have those pair up to just give us the complex here. And if we look at the K values, so this is just KF, formation for the complex, we're going to see that these are all going to be very large numbers, meaning that they're all going to be product favored. So when we look at something like the silver one here, when we look at the next slide, we can see why that this is going to increase the solubility of something like silver chloride. AgCl- is going to be an insoluble salt. So or mostly insoluble, at least, only a small amount of it. So if we look at the picture here, we've got most of it intact as the solid. We only get a little bit of those ions produced. But if we have this react with the ammonia, that silver ion is going to complex with the ammonia to give us that complex ion, which is going to shift, have that reaction shift all the way to the right. So we're going to be removing the silver ion from our dissociation equation. So if we rewrite that one. Oops. So we're going to have this reaction occur when we dissolve silver chloride. Most of it's going to stay as the silver chlorine, like I said. That's why we've only got a little bit of it dissociating here. But now if we mix it with ammonia, what we're going to see is the small amount of this ion that's present is going to complex with that ammonia. And because that equilibrium constant for the complex is so high, pretty much any amount of that silver ion that's present is going to complex with ammonia. So what we're going to see is we'll no longer have Ag+. We'll have it as part of this ion. So we're really removing from the right-hand side of this equilibrium, which is going to cause it to have to shift in that direction to replenish it. So we'll see more and more of this silver chloride is actually going to dissolve there. And that's why we can see initially here, you can kind of think about this as silver chloride in water. Most of it isn't going to dissolve, so that's why we can still see that solid. But as we add the ammonia to it, we're removing this small amount of the silver ion from this equilibrium, having it become this complex. So then more and more of this silver chloride solid is actually going to shift to the right. We'll get it actually to dissolve, and that's why we can see the solution become clear in this case. And then amphoterism essentially just means it can act as an acid or a base. So what we're going to see with things like aluminum and zinc and tin, since they can do kind of either, they'll be soluble in strong acid or strong base, just because they can kind of go in either direction there. But in order to determine if a precipitate is actually going to form, what we're going to do is just compare the KSP, so that solubility product, to Q. And Q is going to be the same thing as we saw with the previous equilibrium, where Q is just going to represent the conditions at that point, whereas K is just going to specify equilibrium. So Q may be equal to or K may be representing equilibrium in the case where those are both equal. And in that case, what it means is the solution is going to be saturated. Essentially means we have the most amount dissolved in that solution that we possibly could have. So it's going to represent equilibrium. And then in the other cases, if Q is less than KSP, we think about what that means is Q is less than KSP. That means we have too much reactant, not enough product. What we're going to see is that substance is then going to shift to the right. So we're going to actually see more and more of that substance will dissolve. Whereas if the opposite's true, if Q is greater than KSP, that means we've got too much dissolved, and we're actually going to have some of it precipitate out of solution. And with it, like I said, Q is just representing the conditions at any moment. So if we look at a question like this one, will a precipitate form when 0.1 liter of 8.0 times 10 to the negative third molar lead 2 nitrate is added to 0.4 liters of 5.0 times 10 to the negative third molar sodium sulfate. And then that gives us the KSP of lead 2 sulfate. What we need to do is kind of just think about each of these solutions. And the lead 2 nitrate is going to give us lead ions. And oops, not 2 negative. Really give us 2 of those nitrate ions. And then the sodium sulfate will give us 2 of the sodium ions and 1 sulfate. So when we're looking at this one, what we need to do is think about what the concentration of each of these ions is going to be. And for lead and sulfate, we get 1 of those ions per molecule. Sodium and nitrate, we get 2 of them per. So we need to consider that, but we also need to consider the volumes. We're mixing these 2 solutions together. So we've got to do M1V1. We've got to look at the dilution equation is equal to M2V2 for each of these. And for both, we'll be solving for M2. We'll be solving for that new concentration. V2 is just going to be the sum of those. So V2 will be 0.5 liters. And then M1V1 will just be equal to those concentrations and volumes, just because the pieces that we're interested in, since we're interested in the lead sulfate, those lead and sulfate ions are just 1-to-1 with the substance they come from. That's why the concentration is just going to be the same. If we were interested in sodium or nitrate, we would have to double this concentration just because we're getting 2 of those ions for every 1 molecule. But since we're interested in the lead and the sulfate, it'll just be M1V1 is equal to M2, and then V2 be the sum of these. So when we go to the next slide, what we'll see when we do that M1V1 equation is that the concentration of the lead 2 ion after we have this all mixed together is going to be 0.0016. And it makes sense it got smaller, 0.008 to 0.0016, because we're taking this and diluting it. So we're going from 0.1 liters to 0.5 liters overall. So the concentration should go down. And then the same thing for the sulfate ion. We're going from 0.4 liters to 0.5, so it's not as drastic of a change. That's why we don't see as drastic of a decrease there. But when we're looking at determining Q, it's just going to be this product of those 2 ion concentrations, because we just have 1 of each of them here. So if we do 0.0016 times 0.004, we get a Q of 6.4 times 10 to the negative 6. And since that's greater than K, that means we've essentially got too much on our product side. We've got too much of these ions. We're going to see some precipitate form in that case. And then with the next one, if you want to practice with this one on your own, it's going to be kind of the same idea. It's just now we're looking at sodium sulfide, or sodium fluoride rather, and calcium nitrate. So with the sodium fluoride, we get Na plus and F minus. With the calcium nitrate, we get Ca2 plus and then 2 of those nitrate ions. But again, we've got to think about what the concentration is going to be after we dilute it. And what we're going to see there is the concentration of the fluoride ion is going to be 0.017, because we've got M1 and V1 here in that first line. V2 is just going to be 0.06 after we add these together. So if we do 0.05 times 0.02, or 2 times 10 to the negative second, same thing, divided by 0.06, we'll get 0.017 for that fluoride ion. And then for the calcium ion, kind of the same idea. It's just we've got 0.01 to start for the liters, 0.01 to start for the concentration as well. So multiply those together, divide by the 0.06 for that new volume. And we'll see that the initial concentration after this is all mixed together is going to be 0.017, or 0.0017, I should say. So when we go to get Q, KSP, we've already seen this one, just to rewrite it to see where these numbers are coming from. We'll have the calcium ion times the fluoride ion. But because the fluoride ion has a -1, we're going to need 2 of these for every 1 calcium. We would just square that concentration. So that's why we've got 0.017 times 0.017. We're really just squaring that piece of it. But again, we're going to see that the Q value we solve for is going to be greater than KSP. So we're going to have too much of the products. We're going to have too much of these ions. We're going to have to shift it back to the left. We're going to see some of that precipitate actually form in this case. And then with this overall, we can use this difference in solubility to selectively isolate and separate out different ions. So if you look here, if we had, let's say, all of these different ions in solution, we could first react it with, or add hydrochloric acid to it. And what we're going to see is when the hydrochloric acid is added, it dissociates into hydrogen ions and chloride ions. So we're going to see those chloride ions are going to be it's just sort of floating around that solution. And what they're going to do is bump into all these positive ions. And if it's a soluble substance, they'll essentially just sort of come together and then come right apart. But if it's an insoluble something like silver chloride or mercury 2 chloride, lead 2 chloride, we'll have those substances stay intact once those chloride ions hit those positive ones. So we'll be able to then filter out these ones. We'll have this stuff precipitate, so we could use a filter, we could decant our solution, but we'll be able to isolate these ones. And then we'll still have everything else dissolved. So we could come through and add hydrogen sulfide in hydrochloric acid. And what we'll see is we'll get this insoluble sulfur compounds to dissolve, or to undissolve, basically, to precipitate out. And then we could filter those. Still have some remaining cations. So we could add ammonium sulfide in a basic solution. And then what we'll see is the insoluble hydroxides, those insoluble sulfides, are then going to precipitate out. Continue through, we can add this phosphate-containing compound to isolate those. And then ultimately, all we'd be left with is these soluble alkali ions. So the group 1 metals, alkali metals, sodium, lithium, potassium, and things like that, as well as the ammonium ion, just because all of those are pretty much always going to be soluble. So there's not really anything we can react them with to form a precipitate like we can for the rest of these.